Hello, welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we had concluded our discussion on the link budget analysis and we had started looking at teletraffic theory. Teletraffic theory is essentially what we said is to model trunking, which is employed by telephone systems and cellular systems to use a limited number of channels to provide services to a large number of users. For instance, we said if there are 100 subscribers, one can have 100 channels, so that's to meet the demands of all particular users, but this is inefficient since the probability that all the users are going to be on a call at some point of time is very small. Hence, instead a more efficient option is to use a much fewer number of channels for a large number of users and statistically multiplex these users. However, we also said that as a result of this efficient system, there is still a small probability that at some point of time the number of users who wish to place a call is greater than the number of channels that are available. This is termed as the blocking probability or the grade of service, and we wanted to employ, our aim was to employ teletraffic theory to compute this blocking probability. And we also said towards this rate we will start characterizing the traffic in a wireless system. We said the traffic in a wireless system is nothing but the user call rate times the average call duration of each user. For instance, if a user is placing 2 calls per hour of average duration 2 minutes each, the traffic per user is 1/15th of an Erlang. We said that this traffic is measured in units of Erlang in honor of the Danish telecom engineer Erlang, who first studied teletraffic theory, proposed teletraffic theory. We also said that the total traffic for n users is n times A naught, where A naught is the per user traffic. And finally, we proceeded to characterize the maximum traffic that can be carried by a system. If there are n channels, then n Erlangs of traffic can be carried by the system. And we also started characterizing this call arrival as a random Poisson process, saying that if there is the call arrival rate is lambda, then the probability that k calls arrive in a time duration t is lambda t to the power of k e to the power of minus lambda t over k factorial. So, let us start here and proceed with today's lecture, essentially, which is we want to start talking about a cellular system. So, we want to talk about cellular system modeling. We said in a cellular system, let there be n channels available, so that a maximum of n users can be connected at any given point of time. All right, and these channels, so there are n channels available, which means a maximum of n users can be supported. That is, a maximum of n users can be connected to the base station or be on a call essentially at any given point of time. Now, what we want to do, however, not all users, not all the n channels are occupied. At any given point of time, probabilistically a few of the n channels are occupied. Hence, let us represent this number of channels that are occupied in a base station at a current instant of time as the state of the wireless communication system. Hence, the state of the wireless communication system of the wireless system is the number of channels occupied at a given point of time. For instance, if 4 channels are occupied, then the system is in state 4. If 5 channels are occupied, the system is in state 5. Remember, since capital N is the maximum number of channels that are available, the system can be in state 0 to n, it cannot be in a state n plus 1, all right. So, system state can be in states S0, S1 up to Sn. S0 denotes the state where no channel is occupied, Sn denotes the state where all channels are occupied, and in between Sk for 0 less than equal to k less than equal to n denotes the state where k of these n channels are occupied. And now we can draw a state space diagram . We can draw a state space diagram for this as follows. I am going to denote the states as follows, so on and so forth, state k, so on and so forth, state n, so what we have here essentially is I have state 0, state 1, state 2, some intermediate state k, and I have the final state n. The system can now transition between these states. For instance, it can transition from state 0 to state 1. That is, if one call arrives in state 0, it can transitions to state 1. If one call departs in state 1, it transitions to state 0, all right, which essentially means when all channels are vacant in state 0, if a call arrives, one channel becomes occupied, so it transitions to state 1. In state 1, where one channel is occupied, if another call arrives, it transitions to state 2. However, if one call departs from state 2, it transitions to state 1, and so on and so forth. Similarly, it transitions from state k minus 1 to k if one call arrives, from k to k plus 1 if one call arrives in state k, from k plus 1 to k if one call departs in state k, and so on, all right. This state representation is also termed as a Markov chain. So, this state representation is essentially termed as a, this is termed as a Markov chain. Remember, we said k is the state where k of the n channels are occupied. Capital N is essentially the state where all the n channels are occupied. And 0 is the state where all channels are vacant, all right. So, 0 is the state where all channels are vacant, n is the state where all channels are occupied, and remember, in state n there is no further transition to n plus 1, that is only n channels are occupied. So, any call that arrives in this system in state n is going to be blocked. So, in state n, any new call will be blocked. And essentially, if we denote the probability of state k by pk, probability by pk, probability of system being in state 0 is p0, probability of system being in state 1 is p1, p2 is p2, probability of system being in state n is pn. Remember, in this state all the calls are blocked, hence this is also termed as the blocking. This is nothing but the blocking probability. Hence, if pk denotes the probability that system is in state k, P n equals probability that system is in state n, which is essentially nothing but which is the So, what we are essentially saying at this point is as follows: if there are n channels, we can think of the system as being in one of the states one of the states S0, S1, Sn, where Sk denotes the state that k channels are occupied. We are going to associate a probability Pk with the state k, that is, with probability Pk the system is in state Sk where k channels are occupied, which means Pn denotes the probability that system is in state n, in which it cannot accept any further calls. Hence, all calls are going to be further calls are going to be blocked. Hence, this is nothing but the blocking probability of the system. This is what we wish to characterize. For this, now we want to proceed with the steady state analysis. What is the probability of, we want to start answering this question, what is the probability of call arrival in a small time interval? So, we want to consider an infinitesimal time interval delta t, consider an infinitesimally small time interval delta t. Probability one call arrives in delta t. Remember, this is given by the Poisson probability that we already talked about. So, probability of one call arrival equals lambda delta t to the power of 1, k equals 1, because it is we are talking about one call, e power minus lambda delta t divided by 1 factorial, which is nothing but lambda delta t into e power minus lambda delta t. Since this lambda delta t is small, this e power lambda minus lambda delta t is approximately equal to 1. Hence, this can be approximated as lambda delta t. That is, probability one call arrives in time delta t is lambda delta t. That is, probability one call arrives in time delta t is lambda delta t. Now, what about call departure? How can we model call departure? Let us consider the average call time as t. In that case, what that means is the call departure rate is nothing but mu, which is 1 bit. So, we can model call departure is a Poisson process with departure rate mu is given as 1 by t. So, we have, if the average call duration is 2 minutes, which corresponds to 2 by 60th of an hour, alright. So, time is 2 by 60, which is 1 over 30, then mu corresponds to 1 over t, which is essentially 30 per hour. So, the call departure rate is the inverse of the average call duration. Hence, now probability, we said this is a Poisson process similar to the call arrival. Hence, the probability that one call departs in a small time interval delta t is nothing but mu times delta t. However, in state k there are k calls and any of these calls can depart. Hence, the probability that one call departs in state k in time delta t is nothing but k times mu delta t. So, probability of one call departure in time delta t is probability one call departs equals mu delta t, where mu is the departure rate. However, in state k, in state k, k channels are occupied. However, in state k we have k channels occupied, which means any of these calls can depart. Hence, the probability of call departure is k times mu delta t. The probability of one call departing in state k is k times mu delta t. Alright. So, now we have characterized call arrival and call departure. We said one call arriving in time delta t is lambda delta t. One call departing in state k, the probability that one call departs in time delta t in state k is k times mu delta t. Now, we want to go back and look at our Markov chain to analyze this. Remember, if we are in, let us consider state k. The system transitions from k minus 1 to k if one call arrives in k minus 1 or one call departs from state k plus 1, or the system is in state k and no call arrives or no call departs. So, let us look at this. Consider time t. System is in state k at time t plus delta t. Let us say system is state S k at time t plus delta t. If one of the following occurs, that is system is in state k minus 1 at time t and one call arrives in this time delta t, then at t plus delta t system will move into state k, that is system is in state k minus 1 at time t and one call arrives. Hence, the system is in state k plus 1 at time k at time t plus delta t if the system is in state k minus 1, that is k minus 1 channels are occupied at time t and one call arrives in time delta t. This probability arrives in delta t. Probability is of this event is nothing but p k minus 1, that is p k minus 1 lambda delta t, where p k minus 1 this denotes probability that the system is in state k minus 1 and lambda delta t denotes probability that one call has arrived. Probability system is in state k minus 1 and lambda delta t probability one call arrives. Similarly, the other case is that system is in state k plus 1 at time t and one call departs in delta t. The other case is system is in state k plus 1 at time t and one call departs in delta t. Probability is nothing but p k plus 1, system is in state k plus 1 and one call departs. Remember, in state k probability that one call departs is k mu dt. In state k plus 1 probability that one call departs is k plus 1 mu delta t. And the other condition, hence we are saying that it can, the other case in which the system ends up in state k at time t plus delta t is if it is at state k plus 1 at time t and in that delta t time one call departs. That probability is p k plus 1 into k plus 1 mu delta t. And the third probability is simple, which is system is in state k and call neither arrives nor departs, hence it continues to be in state k. System, hence the third case is system is in state k and call neither arrives nor departs, and the probability of this is p k into 1 minus lambda delta t minus k mu delta t. What this is saying is p k is the probability that the system is in state k, lambda delta t is the probability one call arrives, k mu delta t is the probability one call departs. Hence, 1 minus lambda delta t minus k mu delta t is the probability that a call neither arrives nor departs. Hence, this is the probability that system is in state k and continues to be in state k at time t plus delta t. Hence, now we have a simple steady state expression for the probabilities which can be written as follows. System is in state k, that is the probability that system is in state k at time t plus delta t is nothing but the probability system is in state k at time t and a call neither arrives nor departs plus probability that the system is in state k minus 1 and one call arrives in delta t plus probability system is in state k plus 1 and one call departs in delta t, that is nothing but p k plus 1 into k plus 1 mu delta t. Hence, rearranging this we arrive at the steady state equation for probabilities, which is lambda plus k mu times p k equals lambda p k minus 1 plus k plus 1 mu this is nothing but the steady state probability equation for our Markov chain. This is the nothing but the steady state probability equation, which is lambda plus k mu times p k equals lambda times p k minus 1 plus k plus 1 mu p k plus 1. There is a special case in this. Consider state 0. We see that in state 0, if you look at state 0 and state 1, we see that in state 0 no call can depart in state 0, only a call can arrive. Hence, there is no moving to the left at state 0 in this Markov chain. Hence, the steady state equation for this can be written as probability that in state it is in state 0 and that no call arrives, which is 1 minus lambda delta t. Lambda delta t is the probability that one call arrives, 1 minus lambda delta t is the probability that no call arrives. So, p 0 into 1 minus lambda delta t is the probability that it continues to be in state 0, which is equal to p 1, the probability that it is in state 1, and one call departs, which is essentially k 1 mu delta t, which is essentially mu dt. So, plus this. So, the probability that it is in state 0 is nothing but probability it is in state 0 at time t, and a call does not arrive, then it continues to be in state 0, or it is in state 1 and then one call departs, in which case it transitions to state 0. Hence, the probability at state 0, that is p 0 at time t plus delta t, p 0 equals p 0 into 1 minus lambda delta t plus p 1 into mu delta t. This can be simplified as follows: p 1 equals lambda by mu p naught. Okay, so, p 1 can be simplified as lambda over mu p naught. Now, let me substitute this in the expression we have here for the general steady state probability equation. Let me consider k equals 1. I can write this as follows: lambda plus mu into p 1 equals lambda p naught plus 2 mu p 2. I will substitute p 1 equals lambda over mu p naught. This is equal to lambda p naught plus 2 mu p 2. Hence, we arrive at lambda square by mu p naught plus lambda p naught equals lambda p naught plus 2 mu p 2. The lambda p naughts cancel. Hence, I have lambda square by mu p naught equals 2 mu p 2. Hence, this can be simplified as p 2 equals 1 over 2 lambda by mu whole square p naught. Okay. So, I can simplify this as p 2, which is now given in terms of p naught as p 2 equals half lambda by mu whole square p naught, and we can also, continuing this way, the general probability of state k is given as follows: p k equals 1 over k factorial lambda by mu to the power of k divided by p naught. This is the steady state probability of state k. This is the steady state probability of state k, which is essentially S k. Okay, now we can employ the fact that the sum of all probabilities have to be 1, because the state can be in 0, 1 up to n states. Hence, the sum of all probabilities has to be 1. Hence, I can say k equals 0 to n p of k equals 1, which essentially implies, now p of k I am going to write it in terms of p of 0 as 1 over k factorial lambda times mu k, which is equal to 1. Hence, I obtain p naught equals 1 over summation and 1 over k factorial lambda by mu to the power of k. Okay. And moreover, now we know that P n is nothing but 1 over n factorial lambda by mu to the power of n P naught, and now I will substitute the expression for P naught to write P n as follows, which is 1 over n factorial lambda by mu to the power of n divided by summation k equals 0 to n 1 over k factorial lambda by mu to the power of k. Thus, we have derived the expression for the blocking probability of this system. This expression is nothing but the expression for the blocking probability as a function of the call arrival rate and call departure rate. Hence, this is nothing but the Erlang, this is termed as the Erlang blocking this is termed as the Erlang blocking probability. One minor recasting of this expression, we know that the lambda equals call arrival rate in this system, that is the net call arrival rate. Mu equals 1 over t, which is call departure rate, hence total traffic, remember from our definition of traffic, total traffic is nothing but call arrival rate into t, which is the average duration of the call, which is nothing but lambda into t is nothing but 1 by mu. Hence, this is nothing but 1 by mu, this is lambda by mu. Hence, what we are saying in this system is that the total traffic is nothing but lambda by mu, which is A. Hence, the total traffic, hence lambda by mu is nothing but A, which is the total traffic. Hence, I can write the expression for blocking probability as simply 1 over n factorial A to the power of n divided by k equals 0 to n 1 by k factorial A to the power of. Hence, this is again the blocking probability as a function of A, which is the total traffic in Erlangs. Okay, so, this is nothing but the total traffic in Erlangs, and this is the blocking probability of the system. Okay. For instance, let us look at an example, and this can be this expression, the blocking probability, or if you look at the blocking, or if you look at the blocking probability, given a blocking probability and n, if you want to compute what the total traffic A is, there are tables available for that. Let us look at a simple example. We have n equals 50 channels P b or Pn equals Pb, which is also denoted by Pb for the blocking probability, equals 10 to the power of minus 2 or essentially 1%. What is the total traffic that can be supported? For that we have to use the tables. What is the, for that we have to use tables, and let us go to this. Here we can see from this table, we look at the green curve for n equals 50 and we look at the blocking probability 10 power minus 2, which is 1%, and we see it intersects the green curve at roughly 0.76, and this is the value of A by n. So, the value of A by n here is essentially 0.76. Hence, essentially I can say that A by n equals 0.76, n equals 50, that is given. Hence, A equals 50 into 0.76, that is 38 Erlangs. Hence, what this says is, at n equals 50 channels and given a blocking probability of 1%, I can support a total traffic of 38 Erlangs, that is at 50 with 50 channels and 1% blocking probability, that is 1% of the time there is a chance that more than 50 users are going to be requesting for calls, or more than 50 users would like to place a call. That probability of that event happening is 1%, and the traffic that can be supported is 38 Erlangs. So, it says that if you tolerate a 1% blocking probability with 50 lines, essentially you can support 38 Erlangs of traffic. Let us consider another a bit more, a slightly more elaborate example. Let us consider a cellular system where each cell has 48 channels. Consider a cellular system with n equals 48 channels per cell, and let the blocking probability P be given as 0.02 or essentially 2%. So, we are considering a cellular system with 48 channels per cell and a blocking probability of 2%. Also given is that the per user traffic in this system is 0.04 Erlangs, all right, and the cell radius is 1 kilometer. Now, if you look at cellular planning, or if you want to talk in the context of cellular system design, what is the number of users that can be supported in a city of area 603 square kilometers. What we are saying is, there are n equals 48 channels available per cell, and the blocking probability that can be tolerated is 2%, and the per user traffic is 0.04 Erlangs, and the cell radius is 1 kilometer. What is the maximum number of users that can be supported in this city, which has an area of 600 kilometer square? And let us look at the solution. We know that n equals, we are given that n equals 48 channels, and the blocking probability P equals 0.02. Hence, the first thing we can do is we have to compute A given Pb and n, and when we use the tables that are available, we can compute this A value as A equals 38.4 Erlangs, that is given now 48 channels and blocking probability 0.02, A equals 0.4 Erlangs. Now, we know that total traffic A equals n times A naught, A equals total traffic and A naught is per user traffic. We are given that A naught is 0.04 Erlangs, we know that A equals 38.4 Erlangs, hence n is nothing but A divided by A naught, which is 38.4 Erlangs divided by 0.04 Erlangs equals 960 users. Look at this large number of users, and this is essentially arising because of trunking. This is nothing but trunking. Why? Because look at this, we have only 48 channels. However, what this says is, if we can tolerate a blocking probability of 2% with 48 channels, I can support 960 users, because the per user traffic is 0.04 Erlangs, which is very low. So, the probability that all users request channels is very low. Hence, I can support an enormous number of users compared to channels I have. This is not possible essentially because of trunking. Now, we have 960 users per cell. We want to compute how many users can be supported. So, this is 960 users per cell, because 48 channels are available per cell. We are given that the cell radius is 1 kilometer. Let us assume the standard hexagonal cell, and if we look at the inscribed circle, this has radius 1 kilometer. The area is nothing but the 6 times the area of this triangle, hence cell area equals 6 into 1 into 1 square root 3, which is equal to 3.46 kilometer square. Hence, number of cells equals city area divided by cell area, which is equal to 603 square kilometers divided by 3.46, which is approximately equal to 174 cells. That is, there can be approximately 174 cells in this city, since 1 kilometer, since you have a cell radius of 1 kilometer. Okay. Essentially, what that means is, number of users that can be supported equals number of cells into users per cell, approximately equals 174 into 960, which is essentially 167,040 users. Hence, the number of users that can be supported in this cellular system is 167,040. This is the total number of users that can be supported in the city. Alright, this is the total number of users that can be supported in this city, and you can see this is essentially because of the trunking gain that is provided by the system. Thus, you have an example of how to plan a cellular system, that is how many users can be supported given the cell radius, that is how to choose these different parameters such as cell radius, number of channels and so on, such that you can support a certain number of users, and it essentially gives you, as a function of these parameters, how do you calculate what users you can support and at what quality of service or what blocking probability or the grade of service. All right. So, this completes our discussion on cellular planning and so on. Just a list of topics that we have covered in this section. We have looked, to conclude, we have looked at wireless propagation models, namely we have looked at the free space propagation, that is the free space propagation formula. We have looked at ground reflection, then we have looked at the Okumura model, and we also looked at the Hata model. Then we in fact went on to look at log normal shadowing and characterize the reliability of this system. Then we characterize the receiver noise power as a function of the power spectral density and bandwidth, and we put all these things together to do a link budget analysis and a planning of a cellular system to account for path losses and everything, which is systematic accounting for the gains and losses in the system. We put this together in as the link budget analysis. And 5, what we considered is we considered trunking and teletraffic theory to model the blocking probability and grade of service in a cellular system. So, that brings us to the end of this module. Thank you very much for your attention.